So we're going to write down our first function, f of x. This one is going to have 3 parts. The first part will be -4, and this will be for x less than or equal to -5. The second part will be 1/2 x plus 3, and this will be for values of x that are between -5 and 2. And then the last piece will be -x minus 1, and this will be for x values that are greater than or equal to 2. First, I'll put my x and my y because we always label our axes, and then I'm also going to put my scale in. For this one, I am going to just go by ones, so I'm going to throw that in there. So to prepare to graph this piecewise function, I'm going to mark off places that I call the breaking points. And those come from these inequalities over here. So the important numbers that we have to look out for are when x is -5 and when x is 2. Those are the numbers that are showing up here. So let's look for when x is -5. This would be -1, -2, -3, -4, -5. Right here, this is when x is -5. And so what I'm going to do is kind of just do a little mark there vertically. And then 2 is here. And so I'm going to mark that as well. So what this is saying is that when x is less than or equal to -5, so over here, we need to graph -4. And then for x values between -5 and 2, so from here to here, we will graph this function, the 1/2 x plus 3. And then lastly, when x is bigger than or equal to 2, so over here, we need to graph this function, -x minus 1. So we're going to graph these 3 different parts on the same graph in different chunks. So let's start over here. We need to graph -4 for this part of the graph. Well, when we have y equals a number, then we get a horizontal line at that number. So -4 is down here, and I'm just going to draw a horizontal line. However, I'm going to do all of this in pencil because the technique I use requires that I erase. So I suggest that you pause this video and you grab a pencil so that you can graph this. Alright, so when y is -4, we're going to draw a horizontal line. So there's my horizontal line, and I'm only graphing it starting at -5 and going left. And then I need to decide if at this breaking point, if I should draw a closed circle or an open circle. So we need to go and look at the symbol that's going on here. Well, this says less than or equal to -5, so that means I'm going to draw a closed circle. So we're done with that part of the graph. Let's move on to the middle one. So it says when x is between -5 up to 2, we need to graph this. But we know how to graph this. This should instantly scream out to you that it's a straight line because it's mx plus b, right? We have mx plus b, and m is 1/2, and b is +3. So remember, we will start with the b because that tells us that we have our y-intercept as 0, 3. So we'll plot our point at 0, 3, which is right here. And then we're going to use the slope to find more points. So this slope tells us to go up 1 and right 2. So from this point here, I'm going to go up 1 and right 2. Then up 1 and right 2, maybe to get some more. And then I could go the other way as well. Let's go left 2 and down 1 just to get some more points in. And then we will draw in our line. All right. And now this is where the erasing comes in. I marked this vertical line as kind of a breaking point. So my graph can't go past this line, and so I need to erase that part that I went over. So there. And then same thing on the right side. I don't want to go past this breaking point, so I'm going to erase everything to the right. And then lastly, I'm going to decide if I want open or closed circles on those breaking points. So let's look over here. Both of the symbols were strictly less than, so they don't have the equals underneath them. That means I need to put open circles at the ends, right at those breaking points. So that's that one. And now we're going to move on to this last chunk. Negative x minus 1 when x is greater than or equal to 2. Well, this is also a straight line. This is, again, mx plus b. This time m is negative 1, and b is also negative 1. So the b tells us we have a y-intercept at 0, negative 1. So let's plot that point, which is right here. And now my slope is negative 1. Well, that's the same as negative 1 over 1. So that means go down 1 and right 1. Down 1, right 1, down 1, right 1. So let's do that. So if we start at this intercept, we want to go down 1, right 1, down 1, right 1, down 1, right 1, and so on. Then let's draw that graph in. And then let's go back and erase the parts that we don't need. So we cannot go past this breaking point. So I'm going to erase this part over here. So that part that I'm erasing right now, that helped us start the graph off. So that's why I like to do this whole erasing technique, is because sometimes the part that I started off with is helpful, but I don't need to have it in my finished graph. Oh, and then we have to decide if we want an open circle or if we want a closed circle at that breaking point. So we have to go back and look at the inequality. Well, this one says greater than or equal to 2. So because of that equals part, that's telling us that we actually want this to be a closed circle right there. So make sure that one is closed. And now, this is all technically one function. It is this f of x piecewise function. Since the piecewise function had 3 parts to it, our graph also has 3 parts to it. So let's practice one more like this down at the bottom. So for part B, our function is going to be g of x, and this is going to just have 2 parts to it. G of x equals negative 4/3 x plus 2 for x not equal to 3, and then 6 for x equals 3. So I'm going to go and put my x and y axes in, and then label my scale. Go by ones. Now this one is a little bit different than the last one because instead of inequality symbols, we have equals and not equals. Let's start with this one here. Of course, we have a line again, mx plus b. And the m value, the slope, is negative 4/3, and the b value is 2. So we know that we have the y-intercept at 0, 2. So let's plot that. That's going to be right here. And then the slope is negative 4/3, so that's telling us to go down 4 and right 3. So from this point, we're going to go down 4, 1, 2, 3, 4, and right 3. Down 4, 1, 2, 3, 4, and right 3. Okay, so that should be good enough. I'll draw in my line now. Now let's look at what the x value is saying. It says we want to graph this line when x is not 3. Well, x is 3 right here. So we want this line to exist as long as x is not 3. So for this value of 3, we need to erase the line. So I'm just going to erase this one point when x is 3 and draw an open circle. So the open circle means that the line's not there. The line's here, and it's also down here, but not at that value, not when x is 3. Well, what do we want to happen when x is 3? That's what this second part is saying. When x equals 3, we just want to plot the number 6. Well, where is the y value of 6? That's up here. So when x is 3, they want the output to be 6. So we'll draw a closed circle there. And this is our graph. We graphed this line when x was not 3, and we graphed this constant for y when x was 3. So that's a couple different types of piecewise functions that you could come across for graphing. And then let's go on to page 4. And on this page we will do some applications of functions. So this first example says, a community college has 30 feet of dividers with which to set off a rectangular area for a student testing center. They'll place the testing center in the corner of the math lab. So I'm just going to draw this before I even read parts A and B and C because it's always helpful to draw pictures when possible. So this will be the math lab. And then it says they're going to put a little testing center in the corner, and they're going to put that in by using these dividers, and there's 30 feet worth of dividers. So let's put this in a corner like this, and these are the dividers. So we don't know what the length and the width are, so for now I'm just going to call this L for the length. And then I could call this side W, but I know that whatever's left of the dividers is how long this is going to be. So we started off with 30 feet, and we'll subtract the L, and that will leave us with the width. So over here, I'm going to call that 30 minus L. So this in here is our testing center. And let's read part A. It says, express the floor area of the testing center as a function of the length of the partition. So this is area, and we're trying to find the area of the testing center. To find area of a rectangle, that's length times width. And it says that we only want to use L. So we won't have L times W, we'll have L times something that has L in it. Well, we already wrote that W equals 30 minus L. So our function, length times width, will really become L times 30 minus L. And then we need to write this as a function. So I'm not going to write A equals this. I'm going to write A of L as a function. Because in here, we put the variable that we're using, and in this case, we're using the variable L. And that's all they wanted us to do for part A. We wrote the floor area as a function of the length. Then part B says find the realistic domain of the function. So theoretically, the domain of this function would be all real numbers because we don't have either of those possible two domain issues that we always look for. Right? We always look for if there's any possible denominators that could be 0. There aren't any here. And then the other thing we always look for is even roots, which we don't have that either. However, since this is a real world scenario, we can find a more specific domain. So what we're saying is, what can we plug in for L, for the variable? Well, we know that L represents the length here. So what's the smallest number that this length could be? Well, of course it can't be negative. That doesn't make sense for a length to be negative. And it can't be 0 either, because if this length were 0, then it wouldn't exist. So we need to have anything bigger than 0. So we'll start at 0 and go up to, well, we know that we only have 30 feet of dividers. So the largest it could be is just under 30, because again, if we used all of the dividers for the length, then there wouldn't be a width. So everything from 0 to 30, and we do not want to include 0 or 30, so we'll put parentheses on each one. And that's our domain. And then part C, the graph shown is the graph of the function that we found in part A. So this is our A of L equals L times 30 minus L. This is already graphed for us. And so the variable is L. So I'm going to, instead of X, let's write an L there. And then the Y value is really this A of L. It says, use this graph to determine the dimensions that maximize the area. And so dimensions mean find the length and the width. And then we want it to maximize the area. Well, we already talked about maximums and minimums in this section. This is, of course, a maximum. And we have L, comma, A of L. So this part represents the area, and this represents the length of the testing center. So the max area is 225 square feet. Right? The Y value is 225 when the length is 15 feet. So we already have the length that we want, and then we just need to find the width. But we know that the width from up here is 30 minus L. So if we plug 15 in for L, we get 30 minus 15, and 30 minus 15 is 15. So from this, we get that the width is 15 feet. So all together, what this is saying is that when you make the length of the dividers 15 feet and you make the width of the dividers 15 feet, then that will maximize the area of the testing center. So that concludes the section 2.1 node outlines.